Hello there and welcome as we start to derive the linear equations of motion. So this is the first part of our advanced higher physics course, and one of the key things we need to be able to look at is deriving the linear equations of motion that you have been using in higher. So the first thing we're going to start with is remember from National 5 that velocity is the rate of change of displacement and acceleration is the rate of change of velocity. Okay, those two are going to become important. Now, if we take our straight line here that we have drawn, I say we have drawn very nicely, and we have our straight line down there, right? Now that straight line, the distance between the two lines marking that, the change in distance of the object travelling down that would be delta s. So that would be our change in displacement of the object travelling, okay? Now, the time it took to travel that distance would be our change in time, delta t. And so we know from National 5 that the change in displacement over the change of time is the average velocity. Okay? If we wanted to work out the instantaneous velocity, we would need to find a point where the time for that would be as small as possible. Okay? And so with that in mind, if we were to look at that, the limit delta s over delta t, with delta t tending towards 0 as small as possible, and that would just serve, the limit function there just serves in order to provide us with the differential form v is ds by dt for the smallest possible time. Okay, so our velocity is the rate of change of displacement over time, v equals ds by dt. Okay, now we know that acceleration is the change in velocity over the change in time. And so using the same limit, with delta t, I've written dt, sorry, hang on a minute. And with delta t tending towards 0 again, to get it as small as possible, acceleration will be equal to dv by dt. Okay? Now, if acceleration is dv by dt and v is ds by dt, then acceleration could also be written as d squared s over dt squared, which is the second derivative of the displacement. Okay? Now what we're going to do is we're going to use these two statements in order to derive the equations of motion. Okay? Now, there are two methods of doing each of these, so we're going to start with differentiation 1. I'm going to start by using the constant of integration method, and then we'll go over and do the limits of integration method as well. Okay, so using our constant of integration, the first thing we're going to do is integrate both sides with respect to t. Okay, so the integral of dv by dt with respect to t is equal to the integral of a dt. These two dt's are going to cancel off, and so you've got the integral dv is equal to the integral of a dt. The integral of dv is just v, and on the other side the integral of a with respect to t is at, but as I said, the constant of integration plus c. Now we're going to use our initial conditions here, which would be that at a time of 0 the velocity would be equal to the initial velocity, which in physics we call u. So at t equals 0, v is equal to u, and so if we substitute in u is equal to a times t would be a times 0, which is 0, plus c, we can therefore say that c equals u, and so this equation becomes v is equal to u plus at, which is the equation of motion that we know from all the way back in National 5. Okay, now if we were going to do this by limits of integration, we would start off with the same process. We're going to integrate both sides with respect to t, dv by dt is equal to the integral of a dt, but this time our integral is going to have limits, so this one is going to go from u to v, and this one here is going to go from 0 to t. Okay, now with that, when you substitute in, those dt's will cancel, and when you go through the integration, you're going to have v going from u to v is equal to at going from 0 to t, which would leave us with v minus u is equal to at. And then when we take the minus u over the other side, we have v equals u plus at. So there's two different methods, but they both give us the same result. Both take us to this equation of motion. Okay, so this is equation 1, this is the first one we've derived. We're going to go on and do equation 2, again by both methods. So, first method, we are using the constant of integration. We're going to integrate both sides with respect to t again, so the integral of ds by dt with respect to t is equal to the integral of v with respect to t, but we've just worked out that v is an equation. So the first thing we do is cancel off those two t's, and then we've got the integral of ds is going to be equal to the integral of u plus at with respect to t. So the integral of ds, and then I'm going to separate out these this bracketed part of the plus, so we're going to have the integral of u dt plus the integral of at dt. Okay, when we then carry through that integration, we're going to have s is equal to ut plus a half, because we've got a squared, bring down the new power, at squared plus c. Our initial conditions at this point would be when t equals 0. We've not travelled anywhere yet, so s equals 0. Okay, and so therefore 0 is equal to 0 plus c. So our c is equal to 0, and our final equation is s equals ut plus a half at squared. Now, I will say it's really important that you show this step where you cancel off the c, and don't just ignore it, because if you follow this method through, you have to show your constant of integration, or you've not properly done the derivation. Okay, it's really important. And if we were going to use our limits for this one, we would start with the same process. We would have the integral of ds by dt with respect to t, and the integral of v with respect to t. We would cancel off those two dt's. And so in your next line, you have the integral from 0 to s ds is equal to the integral from 0 to t of u plus at dt. I'm going to separate that out into two integrals again. So we're going to have from 0 to s ds is equal to the integral from 0 to t of u with respect to t plus the integral from 0 to t of at dt. We do the integration, you're going to have s from 0 to s is equal to ut from 0 to t plus a half at squared from 0 to t. And if you were to work this out, it would be s take away 0, ut take away 0, plus a half at squared take away 0. So we're going to end up with s equals ut plus a half at squared. Okay, it's entirely up to you which method you prefer. And then if we combine those two equations, we're going to be able to solve ourselves for a new equation. So if we start with equation 1, v equals u plus at, and we square both sides, you would get v squared is equal to u plus at all squared. So you need to multiply out the brackets here. So v squared is equal to u plus at, u plus at. So we're going to get u squared plus uat plus uat plus a squared t squared. Okay, Next step I'm going to do is I'm going to combine my like terms together. So we're going to have v squared is equal to u squared plus 2uat plus a squared t squared. Okay, now I'm going to take some factors out of this to sort of try and make it look a little bit nicer. Okay, I'm going to leave the v squared and the u squared alone. But what I'm going to do is I'm going to take out 2 as a factor from this last bit here. And I'm going to take out a, right? And so if I take out 2 and a from 2uat, I get left with ut. And if I take out the 2a from a squared plus t squared, I'm going to have to put in a half, so that when the half is multiplied by the 2, it becomes 1. And I take out a, I get left with a. And I'm going to leave the t squared there because I didn't do anything to it. And you will notice that this here is equal to s. And so v squared is equal to u squared plus 2as. And you'll notice that that is our third equation of motion. I hope this has been helpful for you guys. We've had a quick look at the derivation of the equations of motion. Next video we're going to be looking at how to use this derivation of equations of motion in some questions. We're going to do some worked examples and get you ready for some of the harder stuff. Okay.